This is chapter 5, problem number 28. Last lecture, we talked about centripetal acceleration or circular motion. When we have something running in a circle, okay, for example, we will have a string holding an object and let this object run in this direction. So we are going to feel a tension over here. And the tension over here, the force, tension force, is equal to Newton's second law, ma, where this acceleration is called centripetal acceleration, which is equal to v squared divided by r. Today we're going to talk something a little bit different. It's called gravity. So what is gravity? If you have two objects with some mass, let's say this is with mass 1, m1, this is with mass 2, m2. When you have these two objects, they are going to feel a force. They try to attract each other. Imagine this is a magnet number 1, this is a magnet number 2, and they're in such a direction that they attract each other. So what's going on here? If I increase the power of the magnet or 1 or magnet 2, they are going to attract more. They have a greater force, attraction force between them if this is a magnet. Or what happens if you put them closer? Would that attract even more? Well, based on our experience, yes, if you have two pieces of magnet, if you separate them far apart, you may not feel the force, but if you put them closer, yes, you feel the force. So the force, the attraction force between them, imagine this is a magnet. However, if it's not a magnet, if it's just any two objects with mass, it will work the same way. The force, the attraction force is proportional to the mass of each. So m1 and m2. If m1 is bigger, then the force will be bigger. If m2 is bigger, then the force is bigger. And it will be inversely proportional to the distance square, okay, or to certain power. For example, if the distance between them is smaller, when this number gets smaller, then this whole thing will become bigger. When the r is bigger, when the denominator is bigger, then the whole thing is going to be smaller. So instead of putting it proportional to, we are going to change it. Or we can say it would be equal because it's proportional to, so it should be equal to a proportional constant times this one. All right. So where's this square coming from? Well, we cannot derive it. How do we know it's a square? It's not 2.1, 2.3. We don't. It just followed that way because it always happened, right? So that's why we just write the formula like this. There's no way we can derive it. This would be our magical formula for this week. Let's look at the problem over here. Calculate the force of the Earth's gravity on a spacecraft. 2.0 times the Earth radius. Okay. All right. Calculate the force. Okay. If you look at this formula, force is equal to a constant times m1, m2. Okay. So we can call this is the Earth. The big mass is the Earth, and the spacecraft is over here. So now if you double the radius, for example, if r now become 2r. So what happened with the f? Because you have a square here. So it would become 4r squared. So it would be 4 times smaller. That means when this object moves to a distance, let's say if this is r, this is 2r. If that is 2r, then the force will be a quarter of the original force. Okay. So how do we combine this with the circular motion? Let's look at this. This is the Earth over here. You have a spaceship going around here. I mean a satellite, for example. So how come the satellite, if you go around it, there is a gravity force pulling it in, and that gravity, when that gravity is equal to the centripetal force, when that is the case, that means the satellite can go forever without pulling it onto the Earth. Okay, so when would that happen? That means the force, this force, is equal to the centripetal force, which will be equal to m times, which is this m, times v squared divided by r. If you run faster, if you want the satellite to go faster, you have to move it a little bit outside over here. Because, well, if it's in vacuum, the satellite can just run without using any energy. It can run forever. However, there is a small fraction. So if the satellite doesn't run with any power, then with the small amount of friction, it's going to get a little bit closer every day, a few inches closer to the Earth every day. That's why each satellite should have either some solar power or some type of power to increase the speed a little bit once a while to keep it running on the same orbit. By the way, the lucky number for this one is 6. 6 is your lucky number.